Parallel plate waveguide transverse magnetic mode. We have already studied parallel plate waveguide for transverse electromagnetic waves. Now we are going to study this parallel plate waveguide for transverse magnetic wave. Transverse magnetic means that Hz equals 0, but Ez does not equal 0. And in this case, the general form for the longitudinal electric field component Ez would be Ez as a function of x, y, and z. Would be E small z as a function of x and y multiplied by the propagation function e to the power minus j beta z. From the geometry of the parallel plate waveguide, we can conclude that the derivative with respect to x would be 0. Or in other words, the electric field Ez does not depend on x, it depends on y, because there is variation in y, but there is no variation in x direction, assuming that it extends for very large distance. Okay? So, in this case, the wave equation, which was partial by partial x squared plus partial by partial y squared plus kc squared Ez equals 0, the derivative with respect to x would be 0. So the wave equation would be reduced to be partial squared by partial y squared plus kc squared Ez equals 0, where kc equals the square root k squared minus beta squared. Now by solving this differential equation, we can find out this second order differential equation. So we have two solutions, and each solution will have a constant. So the general solution for this simple wave equation is that Ez as a function of y, because it is independent on x, is a sine kcy plus b cosine kcy. Let us check. If we have taken the first derivative here, it would be cosine kc multiplied by cosine kcy. And the second derivative would be minus kc squared sine kcy. So we have second derivative with respect to y of this function plus kc of this function, kc squared plus of this function. This summation would be 0. In a similar way, the first derivative of this cosine would be minus kc sine. The second derivative would be minus kc squared cosine kcy. So once again, this function satisfies this differential equation. So these two solutions, two independent solutions, represent the solution of this partial differential equation. Now it is required to determine the factors a, b, and also we don't know kc. Okay? Now, by applying the boundary conditions, the boundary condition in our case is that the tangential electric field on the perfect electric conductor is 0. Effectively, Ez, E in that direction, is tangential to the lower plate, as well as it is tangential to the upper plate. So we can say that Ez at y equals 0 should be 0, and Ez at y equal d should be 0 too. So Ez at y equals 0 should be 0, and Ez at y equal d should be 0. So by applying the boundary condition at y equals 0, this sign would be 0. So this would be b cosine 0. Cosine 0 is 1. So the electric field Ez at y equals 0 equal b. And this should be 0. So b should be 0. Okay. On the other hand, at y equal d, now we don't have this component because b equals 0. At y equal d would be a sine kcd. Okay. Now we have two options. Either to say that a equals 0, and in this case Ez would be 0 everywhere, and this is not accepted solution. Otherwise, we can say that sine kcd should be 0, and effectively the sine function, it would be 0 when the argument is 0, or the argument is pi, or 2 pi, or 3 pi, or integer multiple of pi. So by satisfying that sine kcd equals 0 and a is not 0, this means that we have electric field in different values of y. Yeah, it is 0 at y equal d, but we still have electric field Ez between 0 and d. So to satisfy the second boundary condition, we say that kcd should be integer number of y. This integer number n could be 0, 1, 2, 3, and so on. So we have different solutions for this Ez which satisfy the boundary condition. Effectively, any one of these solutions is a correct solution. And these solutions are represents modes. So this solution represents modes of operation of this parallel plate waveguide. So we are going to call this the n mode. So the value of kc in this case would be n pi over d, where n equals 0, 1, 2, 3, and so on. So we have mode 0, we have mode 1, we have mode 2, we have mode 3. We have different modes which can propagate inside this parallel plate waveguide and satisfy the boundary condition. Okay? Alright. So Ez in this case is magnitude A multiplied by sine n pi over d y, where n pi over d is kcn. Okay. Now the propagation constant beta. Beta equals square root of k squared minus kc squared. K squared depends on the operating frequency. K squared is omega squared mu epsilon, and omega is 2 by f. So k squared depends on the operating frequency, and kc depends on the value of n. If the value of k is greater than n pi over d, the propagation constant beta would be real, and this mode will be propagating. If the operating frequency, or if the wave number k is less than n pi over d, then this square root would be imaginary and the propagation constant would be imaginary, and in this case it would be completely attenuating. So if the frequency is greater than the frequency of the nth mode, this nth mode would be propagated. If it is less than the nth mode, this n smooth, it will be stop or evanescent. Okay, and in this case, the electric field mode Ez as a function of x and y would be a magnitude, and because every mode will have its own amplitude, so it would be an sine n by y over d. So the electric field for the nth mode would be an, the longitudinal electric field Ez would be an sine n by over y over d multiplied by e to the power minus g beta z. Once we obtain the longitudinal electric field component, we can obtain the transverse field components. Hx in terms of Ez would be j omega epsilon over kc squared partial Ez by partial y. So by differentiating with respect to y, this sign would be cosine n by y over d, and we have a coefficient n by over d which correspond to kc. So this is actually kc, and we already have kc squared in the denominator. So kc in the numerator and kc squared in the denominator would be only one kc in the denominator, and here we have j omega epsilon. So is j omega epsilon over kc an cosine n by y over d e to the power minus g beta z. On the other hand, the magnetic field, the electric field, EY would be minus j beta over kc squared partial Ez by partial y. In a similar steps, this would be cosine n by y over d. Here we have n by y over d, which is kc over kc squared. So this would be kc minus j beta over kc an cosine n by y over d e to the power minus g beta z. On the other hand, Ex and Hy are proportional to partial Ez by partial x, and because the electric field Ez is independent on x, so the derivative with respect to x here would be 0. So these are the field components of the TM mode in parallel plate waveguide, and the value of Kc is n by over d, where n is 0, 1, 2, 3. Okay. All right. We can see that the lowest order mode in the present case, where n equals 0. If n equals 0, the Ez would be 0, and we have Hx and Ey would be proportional. Cosine 0 is 1. So in this case, Hx would be j omega epsilon over kc multiplied by an, and Ey would be minus j beta over kc multiplied by an, and effectively this dm0 mode is actually the TEM mode, because we have already Hz equals 0. So in TM0 mode, the longitudinal electric field Ez is also 0. So we have Ez equals 0 and Hz equals 0. So the dominant or the lowest order mode, TM mode in parallel plate waveguide, is TM0 mode, which corresponds to the TEM mode. Okay. In this case, the value of Kc equals 0. So beta would be square root of k squared minus kc squared. So it would be k, where it would be omega square root mu epsilon. And the cutoff frequency of the n smooth in terms of Kc, the cutoff frequency is given by Kc over 2 by square root mu epsilon. And Kc is already n by over d. So by replacing Kc to be n by over d, we can see that the cutoff frequency, which means the frequency above it, the mode can propagate, below it, the mode cannot propagate. The cutoff frequency of the parallel plate waveguide for the mode n is n over 2d square root mu epsilon. As an example, assuming that we have 3 millimeters, for example, for the value of d, and we are talking about n equal 1, so the cutoff frequency of TM1 would be 1 over 2 multiplied by 3 millimeter, 3 multiplied by 10 to the power minus 3, 1 over square root mu epsilon, and assume that this is air, so 1 is over square root mu epsilon, it would be 3 to the power 8, 3 to the power 8 over 3 multiplied to the power minus 3, it means that it would be 10 to the power 11, and we already have 1 over 2, so we can say that 10 multiplied by 10 to the power 10, 10 to the power 10 over 5 is 5 multiplied, so it would be 50 gigahertz. So the cutoff frequency of TM1 mode, if we have 3 millimeters spacing, it would be 50 gigahertz. So below 50 gigahertz, we cannot propagate TM1 mode in 3 millimeters. Above 50 gigahertz can propagate. Alright? Okay. The propagation wave number beta equals square root k square minus kc square, and the cutoff frequency of the TM n mode f cutoff is n over 2d square root mu epsilon. At frequencies below the cutoff for a given mode, the propagation constant is purely imaginary, corresponding to rapid or exponentially decaying field. In this case, below the cutoff frequency, this mode is called cutoff mode or evanescent mode, which means that these modes are not propagating. Because of the cutoff frequency below which propagation cannot occur, waveguide modes is analogous to high pass filters. Means that below the cutoff frequency there is no propagation, so there is no power transmission from port 1 to port 2. So in this case, this corresponds to a high pass filter, such that above the frequency it transfers the power, below the cutoff frequency it stops the power. For the case of parallel plate waveguide, we said that the value of beta equals square root k squared minus kc squared, where kc is n by over d, and the magnetic field hx and ey are given by these equations. So we can say that the Tm wave impedance ZTM equals minus ey over hx, which equals beta over omega epsilon, or in other words can be represented as beta eta over k, where eta is the square root mu over epsilon and k is the square root or omega square root mu epsilon. It can be noted that because the wave impedance is proportional to beta, It is pure real if the frequency is greater than the cutoff frequency. On the other hand, it is pure imaginary if the frequency is below the cutoff frequency. Because if the frequency of K is less than Kc, this would be pure imaginary. So in this case, if F is less than Fc, the value of beta would be pure imaginary and the corresponding wave impedance would be pure imaginary. On the other hand, 1 over square root mu epsilon, which corresponds to omega over k, the phase velocity would be omega over beta. And because beta is less than k, because it is k minus something, so beta is less than k. So in this case, this wave velocity omega over beta is less than omega over k. Because, beta is less than k. So the phase velocity omega over beta is greater than omega over k. Because beta is less than k. Beta is less than k. So omega over beta, omega over small quantity, is greater than omega over k. So the phase velocity here equals omega over beta, which is greater than 1 over square root mu epsilon, which corresponds to omega over k, or the phase velocity of light in the medium. So the phase velocity in the TM mode, or the phase velocity of the TM mode in the parallel plate waveguide, is greater than the phase velocity of the light inside the dielectric medium of the waveguide. In a similar way, the guided wavelength, lambda guide, is 2 pi over beta. Once again, it is greater than lambda, which is the free space wavelength. If I have dielectric material of mu and epsilon, and I calculated the wavelength inside this material, which is 2 pi over k, we find that for the TM mode, the guided wavelength is greater than lambda. And similar to the cutoff frequency, we can define the cutoff wavelength. The cutoff wavelength is 2d over n, such that the cutoff wavelength is determined from the cutoff wave number k. We can say that kc equal 2 pi over lambda cutoff. Okay? And kc is already n pi over d. So n pi over d equal 2 pi over lambda cutoff. From this we can say the cutoff wavelength is 2d over n, where n is the number of the mode. If the operating frequency has a cutoff frequency less than, if the operating frequency has a lambda, has a wavelength less than the cutoff frequency, it would be propagating. If it is greater than the cutoff frequency, it would be stopped. Should be noted that the cutoff frequency and cutoff wavelengths are inversely proportional. So the wave would be propagating if the frequency is greater than the cutoff frequency. In terms of the cutoff wavelength, the wave would be propagating if the wavelength is less than the cutoff wavelength. If the wavelength is less than the cutoff wavelength. Alright? Okay. Now, it is interesting to know that The mechanism of the TM mode can be represented as a combination of multiple reflected TEM waves. This can be represented as, if we are saying that Ez equal a magnitude multiplied by sine pi y over d multiplied by e to the power minus g beta z. This is effectively TM1 mode. Effectively, this sine function, it can be expanded as e to the power j pi over d minus e to the power minus j pi over t over 2j. We can say that sine x equal e to the power jx minus e to the power minus jx over 2j. So by expanding, sine pi y over d can be represented as this. Actually, this is a wave propagating in a tilted angle. We have a propagation constant in negative y. We have a propagation constant in negative y in addition to propagation in positive z. So this equation represents a tilted wave propagating with an angle theta, where the propagation constant in y direction is pi over d, and the propagation constant in z direction is beta 1. And because beta 1 equals square root k squared minus pi over d squared, we can say that pi over d squared plus beta 1 squared equals k squared. Means that we have a propagation constant in y pi over d, or in negative y pi over d, and in positive z beta 1. So we have a propagation in z and propagation y, which correspond to a tilted plane wave with an angle theta. This angle theta can be determined as the tan minus 1, the propagation in y over the propagation in z. So we can say that theta equal tan minus 1 pi over d over beta 1. Or in other words, we can say that k sine theta equal pi over d, k cosine theta equal beta 1. So by dividing this over this, pi over d over beta 1, it would be tan theta. Or in other words, theta, it would be tan minus 1 pi over beta 1 d. This is the first component. The second component corresponds to a wave propagating in y direction, in positive y direction, by propagation constant pi over d, and propagates in positive z direction by propagation constant beta 1. So in this case, we have propagating in y and in z. The total propagation will be tilted by an angle theta in this direction. So we have two components, one propagating in negative theta and one propagating in positive theta, and these two components simultaneously correspond to or represent a total field with sinusoidal distribution sin pi y over d, or standing wave sin pi y over d, and propagating in z direction. So effectively, TM1 mode can be represented as a combination of two oblique incident plane wave propagating with angle theta, such that this plane wave should satisfy the boundary condition at each plane, which is the tangential electric field is 0. So we have a plane wave with angle theta here, and reflected here, reflected here, reflected here. On the other hand, we have another plane wave going in this direction. Now, what is the physical meaning of the phase velocity? Effectively, the phase velocity is not the velocity of the TM wave, but is the velocity of the phase of this tilted plane wave. And effectively, this tilted plane wave is propagating with the velocity of the light in the medium. So its propagating velocity is k. So the velocity here is 1 over square root mu epsilon. But the phase is due to the tilted phase front. So the spacing in z direction equal the spacing between the phase front over cosine theta. Or in other words, the phase velocity would equal the velocity inside the medium 1 over square root mu epsilon over cosine theta. So this tilting angle is responsible for increasing the phase velocity in or along the longitudinal direction along the z direction. That's why omega over beta 1 would be 1 over square root mu epsilon cosine theta. So in this case, the propagation along the z direction, which corresponds to the phase velocity of the TM mode, is greater than the velocity of light inside the medium, which is 1 over square root mu. Alright? Okay.